These are notes for the first day of solutions. Some people have problems. Chemists have solutions. Polar. Polar substances have a region that is partially positive and partially negative. This is noted by the Greek lowercase delta, here it is, with a positive sign or a negative sign. So that means it's partially positive on the H's and partially negative on the oxygens. Here are some things that are polar: water, ammonia, acetone, SO2, vitamin C. Ionic compounds have a negative and a positive region also, but the electron is completely transferred, as we learned in bonding. It is not shared as it is in these other compounds. For solubility, which is what we need to know about ionic compounds, you need to use the solubility chart that we use back in the reaction unit. So example, silver chloride, is it soluble or is it insoluble? You'd have to look at the chart. Sodium nitrate, is it soluble or is it insoluble? And when I'm talking about soluble, I mean is it soluble in water? And all sodiums are soluble in water, and so are all nitrates. So sodium nitrate definitely is soluble. Nonpolar. A nonpolar substance does not have a charge distribution of negative and positive. These compounds are 100% covalent. Examples: benzene, there's the benzene right there; paraffin wax, someone's getting their feet waxed; carbon tetrachloride, right there; cholesterol, Homer eating a hamburger; fat, that cat is bulging; vitamin E, those are vitamin E tablets; rocks, sea stars, those are all nonpolar. Like dissolves like. Similar substances tend to dissolve in each other. Polar things tend to dissolve in polar things. Nonpolar tends to dissolve nonpolar. So if you dissolve in something, you're miscible. If you cannot dissolve in something, you're immiscible. So here we have a picture of table salt, which is sodium chloride, and when it dissolves in water, it breaks up into its ions of Na plus and Cl minus, and the reason it does that is that the water molecules surround the Na plus and the Cl minus part. In fact, the Na plus part is surrounded by the oxygens, which are partially negative in water, and the Cl's are surrounded by the hydrogens, which are partially positive. And it appears to disappear according to your eyes, but it's actually dissolved within the water. Here's some oil on top of the water. It is not dissolved in the water, it's obviously floating on top of the water. Like dissolves like. So here's an interesting website you could check out. This little boy is eating cotton candy. He has saliva in his mouth, which is polar, and it's going to dissolve. Well, the saliva actually is polar and nonpolar, and it will dissolve the cotton candy, which has polar molecules in it, the sugar. Solubility. Look at this great big lava lamp. The oil lumps, or whatever they are in there, are insoluble. This person has grease on their hands from fixing a bike chain. You could get that off your hands with oil. Oil dissolves oil. Nonpolar dissolves nonpolar. The leaves on the trees must be nonpolar because when it rains, leaves do not dissolve. Cows tend to excrete a lot of urine and fecal matter. The urine dissolves into the soil, and farmers also use fertilizer, which is similar to that, and dissolves in the soil. The fertilizer, which is made of nitrates, and the urine is really not a good thing to have in the soil because it's soluble and can get in the water table. Hence an outhouse. The stuff in the outhouse could also dissolve into any water aquifer underneath if it is not a properly built one. Here's an animation of polar-nonpolar molecules, but the last time I checked it in 2011, it was not working. Like dissolves like practice. So would acetone, which is polar, dissolve in water? Yes, because water is polar. So you got to remember for a test that water is polar. Would ammonia, which is polar, dissolve in benzene, which is not polar? No, they would be immiscible. Would table salt dissolve in water? Yes, it does. Polar and polar. Sodium nitrate is ionic. It dissolves in water. Does that mean it's polar? It's really ionic. It's at the extreme end of polar. You'd have to use a solubility chart to find that out. This next one, calcium carbonate, which is chalk, does it dissolve in water? It actually is insoluble in water. You'd have to use the solubility chart for that. Not all ionics dissolve in water. Vitamin E is nonpolar. Would that dissolve in fatty tissue? Yes. Fatty tissue is nonpolar. Vitamin C is polar. Would it dissolve in water? Yes, because water is polar. rate of dissolution. So how can we get things to dissolve faster? So dissolution is dissolving, which means you're soluble. So you could increase the surface area. Here we have a circle, magically a square, broken up to more squares and more squares. So the larger the surface area, the more readily it will dissolve, like superfine sugar dissolves really well in water. If you increase the temperature, it tends to help things dissolve at a faster rate. If you agitate or stir things, it also helps to have things dissolve at a quicker rate. Moving on to the next slide. Brief vocabulary. A solution is a homogeneous mixture of two or more substances. A solvent, a substance present in the largest amount when dissolving two or more substances. So the solvent does the dissolving. The solute is the thing being dissolved. This can be a liquid or solid. An aqueous solution is a solution that has water in it. Water is the solvent. More vocab. Miscible. Substances that will dissolve in each other are miscible. If things do not dissolve, they're immiscible. For example, oil and water. So I'm going to give you an example of structure and solubility. Soap and grease. Or you could think of soap and oil, soap and fats, perhaps when you're washing dishes. So here's soap. Soap has a hydrophobic end, which is a non-polar end. It means it doesn't like water. And it has a hydrophilic end, which is an end that loves water. So soap, I'm just saying this jokingly, is bipolar because it has a polar end and a non-polar end. So here we go. We could write this organic molecule a little bit more succinctly like this. We got a polar end and a non-polar end. Well, what does it do when it sees a big drop of grease in the water? Grease is non-polar, but water is polar. The beauty of soap is that it lets you dissolve the non-polar in the polar. So the hydrophobic ends of the soap dissolve in the grease. The hydrophilic ends of the soap dissolve in the water around the outside of the grease blob. Water molecules can surround and dissolve grease. It helps get grease out of your way. It's a wonderful thing. The end of the notes for the intro to